Okay. So I assume that we're going to count in here, but I guess it's not going to be audible. Anyway, so we're going to talk about length dilation, and sometimes you hear people talk about Lorentz length transformations or the Lorentz-Fitzgerald length transformation equation. And when we talk about these things, we talk about the way that an object that's moving relative to an observer is observed. And when I say observed, I don't mean like as an optical illusion. I mean like actually experienced. So if we were to see this spaceship, for example, travel past us as outside observers, what we would see would be a length contraction that's collinear with the direction of travel. So it wouldn't get squished in every direction to just get shrunk down to a point. It would get shortened along the axis in which it's traveling. And this is kind of something that we don't see in sci-fi very much. Like, you think about this, if there was like a Buck Rogers spaceship or a Star Wars spaceship or a Star Trek spaceship that flew past and it looked like this little stumpy thing that got squished along the direction of the axis of travel, everybody would be like, that's stupid. What a dumb special effect. But that's what would happen. And that's why most of these sci-fi shows are actually fantasy shows. And they did try this. There was actually a Star Trek movie, I think it was a Star Trek movie, that came out in the early 80s, maybe late 70s, somewhere around there. And when they flew fast, all the stars got shortened. And people were like, that's not right. That's not the way it works. Everybody knows that when things go fast, they get stretched out horizontally, you know? Kind of like when you watch an Indy race or like a race car thing, everything gets streaked out. Now the truth is, we know, physics people know, that things get stretched out horizontally like that because camera exposure. The camera exposes itself to the light, and the image drags across the exposed camera, whether it's film or whether it's a CCD. It's going to drag across and going to cause a streaking effect, right? That has nothing to do with special relativity. That has to do with the tool of observation, which in this case would be like a camera of some sort. But that's what people believe in because that's what they've seen. And so if you actually do like a proper scientific representation, sci-fi special effects, and something flies at high speeds like this, it should get all stumpy. It should get all short and contracted like this because length dilation is a thing. This length contraction is a thing. We've got a table of values here at the left-hand side that sort of fleshed out that has a list of all of the lengths that an object would experience if it had a rest length, they call it. This rest length or proper length of 2 meters. So if you had a 2 meter long spaceship, that would be the length that would be observed by somebody in the spaceship. So what we said yesterday was that proper measurements, proper time, in this case, proper length, those are the measurements that are made by somebody who's moving along with the experiment or moving along with that environment. And in this case, the experiment is that spaceship. That's the experimental environment that's moving along. That's the place where the observations, or sort of where the moving thing is. That's the proper measurement. So the proper length of the spaceship might be 2 meters, but to us as outside observers, shrunk, smaller, okay? Now again, in our textbooks, our particular textbook, it uses S for stationary instead of P for proper, and it uses M for moving with respect to instead of observed. And I'm okay with moving with respect to as a subscript, and I'm okay with stationary with respect to as a subscript. However, most textbooks don't use those letters. That's why I'm sticking with the P's and the O's. I'm just reiterating that that's the reason why. And that's the only reason why I'm using P's and O's. P for proper and O for observer, okay? And again, you can see that there's sort of a graphical representation to what happens here. I think that what we saw with the graphical representation for time was that the time seemed to really take off at the 0.5 times the speed of light. It looks like this length contraction it's always happening, but it really starts to take off at like 1/8 of the speed of light. And so it's interesting that the two are different, but then again, take a look at the equations. Notice that the gamma factor was in the denominator in the previous version, and it's in the numerator this time. Now we got the observed length, where the square root of 1 minus v squared over c squared, which is still present in this equation. It's just in a different location. Okay? And we're not going through the derivation of this particular equation, but it does take on a similar, but definitely different form. And here's the question though, what is the length of the object? 'Cause I said we like to go to the extremes in these thought experiments. What's the length of the object going to be when you travel at the speed of light? So like if we take this extreme and we say LO is equal to LP times the square root of 1 minus v squared over c squared, if I sub c in instead of the v, what happens inside of the square root? What's the value of that square root? 0, yeah, big goose egg. So I would say LP times 0. And so like at that extreme, you're like, oh my gosh, so if you go at the speed of light, this object would have a length of 0. Well, yeah, that's what we're saying. And that would be a weird idea. I mean, edge on, if you saw this spaceship go past, it wouldn't just be a pancake. I mean, pancake has thickness. This would be a pancake without thickness. Not even a crepe, you know? Like, not even a sheet of paper. And I think that that's a really hard thing to conceptualize, for me at least, because when I think of something that doesn't have a length, I think of a piece of paper. But that piece of paper has thickness. And that's something that I have a hard time wrapping my head around, is this extreme of having no thickness. And you know, the crazy thing is, we could even think about, well, what would that even do to density? That's a whole nother kettle of fish, right? And so this really is like a weird and wild effect, like this idea that this object is getting foreshortened like this. And again, I want to reiterate that this is not an optical illusion. It's not like, oh, it's just the way I see it. Remember, with simultaneity, things are either simultaneous or they are not. They either happen at the same time or they do not. And my perception of simultaneous is different than somebody who's in motion's perception of simultaneous. And we should be okay with that. In this case, it's either the proper length or it's the observed length. And one's not an optical illusion or anything. It's the way that we're going to take in the universe. It really is that length from our perception in the universe. All right, so people say, well, can you prove it? Is there any evidence? Because this is science, it's not philosophy, and philosophy is great, and thought experiments are wonderful. And thought experiments really can take us so far, and they sort of bridge that gap between philosophical thinking and scientific, evidence. And we love that. But in 1964, yeah, so I'm reaching back into the past because I want to say, all the way back as early as 1964, yes. CERN had a beam of pions. They were accelerated at 99.975% of the speed of light. They have a short, unstable lifespan. I mentioned that already in the preamble before recording the video. And it turns out that yes, they decayed at a rate that was consistent with special relativity. Fantastic. So all the way back to 1964. And then the interesting thing is that when they fired off gamma rays, that radiation, because when those particles do decay and they boom, explode like a grenade flying through the air, gamma rays get fired off. And what we said last day was that when headlights on a spaceship are shone out, the headlight light doesn't exceed C, right? And while I think it's great to talk about spaceship headlights, this is the headlights. The gamma rays getting flung off of these decaying particles. These are the headlights on not a spaceship, but on a decaying radioactive particle. And the headlights light didn't exceed C. The gamma rays didn't exceed the speed of light. And so again, even embedded in this, yes, we got the decay rate time dilation thing, but yes, we have support for the postulate for the headlights not going faster than the speed of light. It's just the headlights are gamma rays in this case, right? So, this is one of those things where yesterday I was talking about baseballs and pickup trucks and things, but I want it to dovetail with the real thing of subatomic particles. Not the real thing, the relativistic thing of subatomic particles. Electrons have been accelerated to ridiculous percents of the speed of light. So many nines, and actually, this is an old number. It's gotten even faster. I've had this slideshow for maybe a few years, but we can never get them up to C. And we keep on chugging in more and more and more power. Large Hadron Collider, any other projects beyond, they're going to want bigger and bigger power sources, nuclear reactors. Maybe one day we'll get the fusion reactor going and we'll have that hooked up. But all predictions say we're not going to get past C. We just keep on chugging in energy into this thing. And if you ever do get to visit a particle accelerator, it really is neat. I've only actually been to a linear one. I went to one in California. My sister-in-law was going to school in Stanford down there. Got to see the linear particle accelerator. It was really cool. It was a tunnel, and from what I understand, people go for jogs there now because it's not being used as a particle accelerator. But just to think that there were electromagnetic fields and all these coils and all of that using essentially force fields. Like in biology, they talk about peristaltic action, where the muscles contract and they push the food through the system. Can you imagine having electromagnetic peristalsis that just like pushes the particles faster and faster and faster and faster through the system? What a crazy thing. And with a linear particle accelerator, it makes me think of a digestive tract that goes from one end to another. With a cyclic particle accelerator, can you imagine? I don't want to be too gross about this, but the anus meets the mouth, and it just keeps on going faster and faster and faster and faster around the circle, That's really cool. And then eventually you fire it off of the circular track, and you blast it into whatever it is that you're trying to blast it into, and you check to see what happens to the particles. Like, this is kind of a neat thing. But we keep on getting things faster and faster, never up to speed. Muons, this is another particle. And they go through a decay process as well. But as they fly through space at a high speed, again, their lifespan has been shown to be longer from the lab observer reference frame than if they were just sitting still. If they're flying through space, they last longer from our perspective than if they were just sitting still. So it's just good to have all these little bits of evidence. I just said that. And then finally, and I still am trying to reach back to the past to say that yes, we've really been on this for a while, because there's always somebody like the equivalent of a Flat Earth Society person that wants to say, no, you can't prove this. But yes, even as far back to the 1970s, University of Maryland was flying atomic clocks at high speeds. And again, the amount that those atomic clocks were off relative to clocks that were sitting on Earth's surface was within a 1% agreement with relativity, even with the instrumentation they had at the time. So I'm just throwing this out there that this is something that, yes, we've had evidence for a long time. Yes, we could throw up a whole bunch more evidences that are even more recent than the 60s and 70s. But I'm throwing the 60s and 70s ones up there. First, because they won't go out of date. But two, because I want to make sure it's clear that we've believed this for a long time. Now, if you're somebody who's going for a school picture, you can head out. You'll have to catch up on the video when you come back. I'm so sorry.